So today I'm going to talk about hybrid data center networks, what those mean, why people might be interested in building them, and some experimental work on actually constructing them and making some measurements with them. As Madeline said, this is a very large project, so I'm speaking for many people. There's two main components of this. The control plane is called REACTOR, and that's a mostly computer science driven effort by a variety of both graduate students and professors. And then I'm also going to talk about an optical circuit switch that we've characterized to use in hybrid data center networks. And both the students and the senior faculty involved in that. So the outline of my talk is I'm not going to spend a lot of time on scale-out data centers. We've heard quite a bit of that yesterday about the motivation of what the issues are as you try to scale out data centers to much larger number of end hosts. And then I'll spend quite a bit of time on the motivation for why you might be interested in building a hybrid network where you route some of the traffic using a standard packet switch network and you route some of the traffic using circuits. And then I'm going to spend most of the time on the research about how you actually use circuits in a packet switched environment in data centers. Unlike HPC, people are comfortable with a programming methodology based off of Linux and so on. So you basically, if you're going to use circuits, you have to hide it from the application, so the application doesn't even know that you're running circuits. I then want to discuss kind of the yin and yang between what people try to do in terms of all the pacing that we talked about yesterday in terms of trying to get smooth traffic. We actually want to do the exact opposite when circuits. We want to batch stuff up and create bursts so that we can use the circuits efficiently, and how you might go about doing that. As everyone knows, the biggest issue with circuits is the actual scheduling, how you get the traffic, how you estimate the traffic, and then how you actually take that estimate of the traffic and create a schedule. And then I'll talk about the implementation of the optical circuit switch. Okay. So as we all know, scale-out data centers have basically are the backbone or the workhorse of the cloud. They're massive. They have a large number of end hosts in excess of 100,000. The applications that are run, particularly in a multi-tenant, you don't even know what applications are being run on them, so you don't have a lot of knowledge about what kind of network or what kind of demand you're going to have from one time to the next. This is one of the key differentiators between trying to make a network for data centers versus a network for perhaps tightly coupled HPC applications, where you do have quite a bit of knowledge about the underlying workloads, and you can use that knowledge in the compilation process to be able to set up the network. The requirements of these are a very large bisection bandwidth, low efficiency, reliability. That reliability means that most of these data centers are multi-rooted, meaning that they have multiple connections from one level to the other for redundancy. And of course, like all networks and all technology, you're constrained by power, cost, and complexity. So we've seen many of these. I'm not going to spend a lot of time on this. We saw a nice keynote from Cisco yesterday about levels of scale-out networks. The take-home message I want to in this slide is that as you add layers, you add more and more complexity. And particularly if you're building a full bisection bandwidth fat tree, which is one of the standard types of architectures that are used in data centers, that complexity translates to significant scaling in terms of the number of ports, and particularly with respect to the optics involved, the number of transceivers. So the number of components is a very strong function of the number of layers that you use in your network, and that's shown here in the next slide. These are just representative data. These numbers come from, there's lots of sources for these numbers in terms of the number of ports and the cabling complexity of fat tree networks. This is very well known, but it's still useful to put up the numbers because at first glance they can be somewhat staggering. So if you have a 10G network and you have 27K nodes, you have about 130,000 ports in your network to support those 30K nodes. And the way we like to think about it in terms of the motivation for why you might want to use optical circuit switching in a data center is for every single port at an end host, you require 5 transceivers in the core to support that one end host port. Now, a 3-level network can support 27K nodes. Larger data centers cannot get, at least today, large enough radix switches to go beyond that, which means they have to go up to a 5-level network. And if you go up to a 5-level network, then the number of transceivers that you need in the core to support one end host port goes up to 9. Now that's getting pretty expensive, which means that from your networking cost, right, you got 9 transceivers for every end host in your network, okay? And the question is there a better way or a more efficient way to be able to build a network where you can reduce some of this complexity? So basically what happens is you want to run faster and you want to have more fault tolerance. Faster and more fault tolerance means smaller switch radix, okay? And what that means is more layers in your network and more cost. So that's one motivation for why you might want to look at different ways of switching your data within a data center. Another way of looking at it is to actually look at the type of traffic that is run on the network. That's shown in the next slide. This was animated. We had a little bit of a problem, so it's kind of a big blast. But if you look at the type of traffic that is run on the data center, you can very crudely classify it into, on your left, is more network-centric traffic. This is very nicely behaved, well statistically multiplexed traffic that you might see at an aggregation level or above in some network, okay? Now, as you move from that very nicely behaved traffic after it's been aggregated at several levels, and you start pushing back closer and closer and closer to the processor, through the NIC all the way maybe onto a core, what you see is traffic patterns that are much more similar to this traffic pattern. These are traffic patterns that people see in HPC. They're highly correlated, meaning that at any given instant, one processor only wants to talk to another processor in their HPC network, or within a data center, one end host only wants to talk to one end host. So what ends up happening is that data center workloads can vary across this whole space. When you're running applications like Hadoop or Sort, a lot of that traffic is correlated, and you begin to see patterns like this. So just for reference, this is the source destination. Light means more traffic, dark means less traffic, okay? And if you actually take these two things and you kind of say, this is kind of what you see in data centers. You see this mixture of traffic that has commonalities with wide area traffic, and you see some traffic that has similarities to traffic that might be in HPC. And the question is, what do you do with that? Now, what's interesting about working in data centers is there's very, very little published data on what these traffic patterns are. But Microsoft actually did publish one traffic demand matrix about 3 years ago, and there it is. So if you look at this published result, you can kind of look at it and kind of go, okay, it's a little bit of this and a little bit of that. That one insight is the primary motivation for thinking about using hybrid networks. And to emphasize that point, what I want to do is I want to take all of these n by n, so there's n squared of these, and I want to ask at any time instant that I choose to generate some sort of traffic matrix in my network, I want to rank order those connections in terms of the total amount of data that I need to move from one end host to another. And if I do that for certain kinds of workloads, I get something like this. And again, everything in data centers depends on your application. A hand may come up and go, you know, our traffic doesn't look anything like that. But for a lot of data analytics, what you end up seeing is out of the total possible n-squared connections in that traffic matrix, only a very small subset of those connections are carrying a significant fraction of the overall traffic. Okay? So you look at this and you say, that number, if this is n squared, maybe that number is n. We would love that number to be 1, but it's not. Okay? But whatever that number is, that traffic you would like to be able to get on the circuit, because there's only a few of those, so you're going to make a few circuit connections. And then all of this other traffic, okay, which in terms of the total number of connections that the network needs to support is the majority of the connections. Those connections, which carry a significantly smaller portion of the traffic, are routed over the packet switch. Okay? And that's the principal motivation for studying hybrid networks. Okay? If you run data centers or if you run applications that you don't have this power law dependence, okay? In other words, in data centers, there's this kind of heuristic rule that says 80% of your traffic is carried in 20% of your connections. It might go 90-10. If you don't have that, then this might not work at all. Okay? So this is a significant assumption about the nature of the traffic in order for hybrid networking to work. But if you make that assumption, then it's not difficult to understand what you might want to do. We're looking at basically the top of rack switch. And basically, if you have your packet switch network coming off your top of rack switch, you have an overlay network. Meaning that for every single port of your top of rack switch, it's routed to both a packet switch network and it's routed to an optical circuit switch network or just a circuit switch network. Okay? So the circuit switching, basically, the reason you want to do it is for the same reasons that Amin talked about yesterday. In a circuit switch, you can decouple the control plane from the data plane. The control plane can run much slower than the data plane in terms of the speed of its response. And you would use it for persistent high volume traffic within your data center. Okay? The packet switching basically handles the tail of that demand matrix that I talked about in the previous slide. And this is crucial, and I'll continue to emphasize this, because you have a hybrid network, you don't need to have a schedule where the entire traffic matrix is scheduled over the circuit switch. Okay? And there's many reasons why this is important. The most important reason for us is that takes a long time to do. So the fact that you can get an approximate estimate of the traffic, schedule that estimate over the circuit switch, and then whatever is left over that you didn't get right, you route over the packet switch, gives you a great deal of freedom in terms of your algorithm to actually be able to calculate the circuit switch schedule. And that's critical if you're actually going to try to get this implemented in real hardware. Okay, so having said that, now let's look at some of how this might work. So you've got your top of rack switch. You have your optical circuit switch. You want high port count. You want fast switching speed. Now, fast is a relative term. I'm going to explain what we mean by fast. But it turns out that at least for 10G traffic, we don't believe that that circuit switch needs to be any faster than the order of microseconds, because everything else in the network is running at about that speed. And critically, if you want to build this, you want low loss, and I'll talk about that a little bit later. What you need, though, which is critical, is you need circuit-enabled Tor switches, and that's going to be the first of one of the two large research projects. Is that, again, as I said, using circuits which require synchronization in terms of when the circuits are available and not available requires implementing synchronization in a packet-based world, which is designed not to be synchronized. And then finally, this is just one of the advantages of doing this is if you can route the bulk of your traffic over the circuit switch, then the packet switch can be under provisioned. It can handle your latency sensitive traffic. You have a lot more flexibility. For us, it turns out that for TCP/IP applications, we can actually send the acknowledgements back over the low latency packet-based network. So we have lots of freedom in terms of how we partition these. Okay, so with that, there are many significant research issues in trying to actually implement this within the confines of standard data centers, which means Linux kernels. And the first one that I'm going to talk about is how you actually implement circuits in a packet-based world. And and so to do that, and I apologize again for the animation, this is one of the ways that you can envision how you go from a packet-based world to a circuit-based world. So what I'm showing here on your left is a standard switch. And a standard switch is nothing more than a cross-connect with some fast memory, all integrated. One of the ideas of creating circuits is actually to pull that memory out of the switch and push it to the end host. So as opposed to queuing in various stages on the network, right, you're now going to try to set up your queues either at a top of rack switch before it goes, or in the extreme case, pushing the queues all the way to the end host. And I'll show you what I mean. So in the extreme case, you try to push that memory all the way out to the end host, completely hollow out the network, and have no state in it, ideally. Okay? So so how does that look? It looks like this. So here are 6 end hosts. And now I'm showing you, and you can think of these as hosts or TORs. For now, let's just think of them as end hosts. And the end hosts are dual homed, meaning that they have a connection to an electrical packet switch, and all 6 of these have a connection to an electrical packet switch. So if this thing didn't even exist, you'd have a standard packet switch network. Okay? But in addition to their standard connection to an electrical packet switch network, they also have a connection to an optical circuit switch network, or just a circuit switch network. In this diagram, we're showing that you don't need to have a one-to-one port mapping between the output ports of the end host and the ports of the optical circuit switch. And this is an issue because large port count optical circuit switches tend to be problematic to build. So you could actually have a smaller radix optical circuit switch, but then you would need a multiplexer. For all of the results that we're going to show in our work, K and N are actually equal, meaning the number of ports that we go up to the packet switch are the same as the number of ports to the circuit switch. So in order to be able to implement this, one of the key things is, notice that there's 2 things right here. So we actually have to have a separate queue for the stuff that's going out over the packet switch and the stuff that's going out over the circuit switch. Okay? So how does that work? Well, if this is an end host, then that must be implemented at the NIC. So in order to be able to do this, you have to have the ability to be able to queue up different classes of traffic. Class A, send out on the circuit. Class B, send out on the packet. Okay? So if I'm Google, maybe I want to send out all of my backhaul and YouTube over the circuit because I don't have latency requirements and this big bulk transfer. And maybe all the little stuff like mail and so on I would send over packets. Okay? But in order to do that all the way at the end host, you need to be able to develop queues, and then you need to be able to pull those queues to drain that information into the circuit switch or into the packet switch. So one of the key enabling technologies in order for this to work is smart NICs. And unfortunately, a lot of the NICs right now have a limited capability to do this. Okay? And I'll talk about that. So there is a microcontroller and so on. So this is an essential feature for hybrid networking to work. There has to be a way of classifying the traffic and deciding what part of the network it's routed over. And that can either be done at say a TOR switch level, or it could be done at an end host level. Okay? So this is what we built to test this. Actually, let me go forward and then I'll go backwards. So this is the system to set up. Because people don't believe that optical circuit switching can actually work, we are actually started with an electrical circuit switch. So in this test bed, this center piece is an electrical circuit switch. This is a MindSpeed 48-port 10G electrical circuit switch. That's a custom board that we worked on MindSpeed to develop. These 2 things are Vertex 6s. These Vertex 6s have 24 ports of 10G I/O. So we hook up part of that to the circuit switch, and then the other ports here, these are 10G ports on this side and on this side. Those are connected up to the end hosts, and those are connected up to the packet switch. So every single end host has a packet-based connection through the network, and it has a circuit-based connection through the network. Okay? So now let me just step back and show you what that looks like. Here are 4 end hosts on one side connected to one vertex 6. On the other side, we have another 4 end hosts connected to another vertex 6. Here's the cross-point switch from MindSpeed, and here's the hybrid network. There's a circuit switch and a packet switch running in tandem, connecting these 8 end hosts. This is showing the data path and the control path. Right now, what we do is we aren't doing a real-time classification. We will get a schedule. We will load the schedule into the circuit switch, and based off of, for now, actually end destination addresses, we'll decide whether or not to route over the electrical switch, over the electrical packet switch, or the electrical circuit switch. So that's what the testbed components look like for the REACTOR project. That's, as I showed, is the actual implementation. Now let's discuss how this actually works in practice. In order to be able to use commodity hardware, you have to use standard protocols. We're not rewriting a protocol. For this, the reason we settled on 8 is because there is a IEEE standard, which is called priority flow control, which means you can preferentially pull queues at the NIC level. This is what we're using. So I have 8 end host queues. They're maintained by the operating system. They're non-real time. But once I set up the queues, I can pause and unpause those queues in real time using the control plane firmware that's written on the vertex 6 to access those queues that are sitting on our Intel NICs at our end hosts. This is the speed at which, if I ask them stop the queue, in other words, stop sending, this is the off latency that we get measured from the time we issue the command, stop sending, until the time it actually stops sending. The issue here is, remember, there's always a synchronization issue. So we're sending 1,500 byte MTU packets, and depending on where I send that stop signal within that packet, it may decide to finish the transmission of that one packet, or if I'm late in the overall packet length, it may decide to send another one, even after I tell it to stop. We have no control over that, unfortunately. That's a hardware decision made at the NIC level, and that's why you see this off latency, but it is bounded, meaning that no matter when we tell it to stop, within 2.5 microseconds, it will have stopped. Okay? So even though you get this discontinuity, and this is happening because as you get closer and closer to the end, it's finally making a decision saying, I can't turn off that packet, I'm going to send another one. So that's why it jumps up again. Okay? The on latency is actually much more stable. And so here's the off latency. And the students who involved in this actually figured out why this is occurring. So now they can actually map why this happens. And the on latency is more stable. So if you actually look at what this looks like when you actually try to pull these packets, hopefully you can see this. The dashed dot line is when I tell it to turn on. And you can see there's a little bit of latency from the time I actually ask it to turn on until it actually turns on. And the dots are the turn off command. So what you're seeing here is a sequential polling of those queues coming out of the end host NIC going up to the electrical circuit switch. And these are the 8 queues that we have. And it's not easy to see, but you actually can see variance. If you look at when this one stopped, here relative to when this one stopped, this actually took a longer time to stop than it took for this one. And again, that's because of how the hardware in the NIC is deciding that when you issue the command, is it actually going to send the next packet out, or is it going to just terminate the packet that is in the buffer at that point? Okay, so those are the measured results for REACTOR. The next thing I want to talk about is all of this is predicated on the ability to be able to control the burstiness of the traffic. So we heard about TCP pacing yesterday. Think of what we're trying to do as the exact opposite of TCP pacing. So much of the effort in trying to regularize the traffic so that we don't overload the queues in a packet-based network is trying to get the traffic smooth for using a variety of hardware and software mechanisms. We want to do the exact opposite, now careful, for the traffic that is destined for the circuit switch. We don't do this for the packet network, okay? In fact, we want to do the exact opposite for the packet network. But if it's lightly loaded, we're not as worried about this. So we want to be able to control the burst length. And what's interesting about this is we have several knobs that can do that, okay? So let's first talk about where that comes from. So the issue of controlling the burst directly affects how fast you want to run the circuit switch. So the longer the burst I can have, the more I can amortize the cost of the setup and teardown of the switch over the length of the burst. That seems pretty clear. But if I make my burst too long, because I'm in a TCP IP environment, then I'm going to hit my congestion window and TCP will start rearing its ugly head. So we're kind of bounded that we'd like to be able to burst as long as the burst doesn't affect end-to-end performance, but we can't burst so long that TCP begins to bother us. So we call that flying under the radar, meaning that from the application side, it never knows that we're setting up and tearing down circuits. It never sees it because we set up and tear down the circuits on a time scale that TCP isn't sensitive to. Okay? So that then defines how fast the circuit switch needs to be. Okay? And you basically try to match the speed of the circuit switch to the burstiness of the traffic. What determines the burstiness? Obviously, where the circuit switch is deployed. In other words, if I'm deploying a circuit switch, an optical circuit switch, way up in the aggregation of the core, that traffic is sufficiently smooth, so I only need to make decisions on routing maybe on a second time scale. If you recall Amin's talk yesterday on the B4 network from Google, their control plane, at least what he said yesterday, is running on about a minute time scale. Okay? That's because that traffic is so heavily aggregated that the fluctuations in it they can deal with on a minute time scale. How fast would a circuit switch have to be if you were that far up in the network? 1 second's plenty fast enough because the control plane isn't reacting any faster than that. Okay? So that's why where you are in the network determines how fast your circuit switch needs to be. It's obviously application dependent. Certain applications like the burst, as I said, if you're running Hadoop or a sort algorithm, they tend to have more correlated traffic. If you're running memcache in like Facebook, it's highly independent. Okay? So all to all versus highly correlated. Also the OS, TCP, and the NIC. And the NIC is a very interesting thing that we found out. And let me just talk about that. So let's first look at how fast is fast enough. So this curve is showing the burst length. If you want to translate it into microseconds, we're running 1,500 byte MTUs at 10 gigabits per second. That's about 1.2 microseconds. So if you multiply this out by 1.2, you'd get the x-axis in microseconds. But this is independent. Using a burst length in terms of packets, it's independent. And these are 3 different workloads that we've used in the past for other types of optical circuit switches in Mordia. And what I want to pay attention to is this is called the cumulative probability distribution. So basically, if I draw a line at 50% here, basically it's saying half the time for this type of traffic, half the time it's going to burst longer than 50 microseconds. That's what that curve's saying. So this is quantitative data in terms of what happens in terms of how the workloads run and how they will burst traffic into the network. Okay? The interesting thing is that much of this delay, or much of this, is coming from decisions that are made inside the NIC associated with its ability to be able to saturate a 10G link. Meaning that in order for the NIC to be efficient, irrespective of what the underlying application is, it's going to batch. It's going to deliberately burst because in order for it to be efficient, all right, it can't send individual packets out on the wire. All right? And that's something we didn't know until we started this project. This is a blessing and a curse. For us, it's a blessing. For other people, it might be a curse. Okay? And the ability to be able to actually manipulate that in hardware, I think, is going to be a key functionality. So the hardware, at least standard NIC hardware, will burst because it needs to burst in order to be efficient. You can also, and let me talk about what that means with respect to the traffic coherence. So when we burst, we can move this line. So this line dictates the number of circuit connections I need to make. If I speed up the circuit switch, then I can cover more of this total traffic. These are all the n-squared connections that I need to make within my network. If I run a faster circuit switch, I can cover more of that total demand with my circuit. So irrespective of what the burstiness is, faster is always better. But faster isn't necessarily, you don't necessarily need it to be fast enough to cover the complete number of connections. So this is just showing that as I begin to move this around, I can have fewer circuits. I cover less of the network, which means more of it has to get routed up the packet, depending on if I have different traffic patterns. So this is the key thing here, is if I have different traffic patterns, then my assumption of how much I can route over the circuit switch may change. And of course, higher data rate per port, this really, depending on if the higher data rate per port doesn't affect this distribution, then it is still the case that the same number of connections can support that higher data rate. And what's interesting about optical circuit switching is that the rate at which you run on each port is decoupled from the NIC, meaning that for some circuit switches, the amount of data you stick in a port could be 1G, it could be 10G, it could be 1 tera. The optical circuit switch doesn't care. So as the demand scales up, it's you can still support that same circuit switch traffic using the same type of optical circuit switch. Okay. So one of the ways that you can control burstiness and adjust the number of connections that the circuit switch needs to support is right at the hardware. Another way, of course, is doing traffic conditioning. So you can think of this as actually traffic management at the end host. In other words, have the applications actually deliberately burst under your control. Again, you always have to be cognizant that if you slow these things down too much, then you'll start hitting the congestion window and you'll have problems. But you can induce correlation. You can induce correlation to sort. And what that means is you can actually get burst sizes. Remember that the burst sizes I showed before, that the hardware, that was measured in tens of packets. These burst sizes are in kilobytes. Okay? So you can get significantly long bursts from your software through the network and still not have TCP/IP know what you're doing. Okay? And this is a reference to a paper published on this, bullet trains. And what this basically means for people who are familiar with Poisson traffic is I can guarantee you at the level we're looking, the Poisson traffic model does not work. Okay, you see these correlated bursts and so on, and we actually don't want it to work, right? We want it to burst. It doesn't work, and we want to take advantage of that to set up our circuits. Okay, so that was the outline of the persistence of traffic. Now let's talk about the scheduling problem. And the scheduling problem really, as far as we are concerned, really is the long pole in the overall approach. Let's just talk about this, and I apologize that the animation here isn't working, but let me just walk you through this. For people who were here last year, Nathan Farrington presented part of the work I'm about to show in the next 3 slides based off of a paper where he presented a complete schedule for an optical circuit switch. I want to go through that and discuss this. TM stands for the traffic matrix. So the steps are you have to figure out what's going on in your network. You have to calculate a schedule based off of what you're doing, and then you have to actually reconfigure the switch. And the problem is that in our previous realizations of this, which was published about 3 years ago or 4 years ago now, called Helios, we did this, but we only set one partial schedule based off of that. So that's called hotspot scheduling. So in other words, you observe, but based off of that observation, you have one what's called permutation matrix. You can only put, for this 5 by 5 matrix, you can only make 5 connections at any given instant of time. Okay, that's just a condition of how any cross point works. So here's 5 connections on that 5 by 5 matrix. For hotspot scheduling, that's all you have. It would be much better to be able to take that time and slice it into submatrices, each one of them which is still a permutation matrix, and then weight those permutation matrices by a time. So when you do that, you cover much more of the total traffic matrix. And in fact, what Nathan showed last year is you can completely decompose the traffic matrix into a set of permutation matrices with weights. Okay? So here is the traffic matrix. Here's the permutation matrix for one permutation matrix. If you just did this, you might be able to pull out, I don't know, 10% of the traffic with maybe one hotspot in your network. But it's much better to take that same traffic matrix and decompose it into a sum of permutation matrices, where each one of these, again, is this row column limited. You can only put 5 limited by, it can't have in the same column or the same row. And then you weight these by the time that you keep it. So in doing that, you can use your circuit switch by going through multiple permutation matrices and changing them, the weights. So this is similar to weighted round robin, but we don't do a complete round robin. We just weight parts of the permutation matrix. So how is this approach different than the approach that Nathan talked about? Well, okay, so this is the complete one, is you take your traffic matrix, you decompose it, and here are these submatrices, each one of them weighted by time, and then what you find out is this entire sum of weighted submatrices sums to the traffic matrix, and then you execute these in hardware. So if I didn't have the packet switch, I must do this because this is the only way I can satisfy the traffic matrix. Okay? But I do have the packet switch. So for perfect decomposition, I might need all of these. But as I said, is if 3 of these, in this case, can cover 70% of the traffic because of this correlation, then I can schedule 3 permutation matrices over the circuit switch, get 60 or 70% of the traffic for that time over the circuit switch, and then the remainder I'll just route over the packet switch. Now why is that such an advantage? Because the computation time for this, Birkhoff von Neumann is a very well understood algorithm, okay? This takes a long time. This is not a full decomposition of the matrix. It's a partial decomposition. How long does that take? Well, that's a very interesting research question, right? But I can assure you that it's a lot faster for me to get 3 of them than all of them, okay? How much faster and how much of the total traffic matrix I can cover with a given number of submatrices, that is a very interesting research question that we're currently trying to figure out. Okay, so the scheduling summary, clearly the faster the circuit switch, the more of the overall matrix can be scheduled using circuits. The schedule for the circuit switch does not need to be perfect, and this is a key insight for hybrid networking. Most people, when they say, oh, it's NP hard, you can't do it. I'm not solving the NP hard problem because I'm not getting a full schedule. I'm getting a partial schedule. Okay? So the schedule for the circuit switch does not need to be perfect. The rest is routed over the packet switch. Okay. So I've talked about how you can do circuits in a packet-based world. I've talked about this relationship that we want to do the exact opposite of what a lot of people want to do when you're running packets, which means we want to develop burstiness. We want to develop that burstiness so we efficiently use our circuits, but not so long that we run into problems with TCP/IP. The last part of my talk is how we actually build an optical circuit switch to do this. So this then, optical circuit switching. So first of all, the history of circuit switching. Circuit switching, optical circuit switching was, for data centers, might have been new 3 years ago. It wasn't new as an idea. Several national labs and IBM in the mid-2000s started to investigate optical circuit switching for HPC applications. And they realized, again, because they had these highly correlated flows and they had knowledge about what was being run on their network, that that made a lot of sense. Because I can extract that knowledge out to get that schedule to schedule the circuit switch. So based off of that work about 3 years ago, several independent groups came up with ideas of how to use optical circuit switching within data centers. But the key insight to understand is we don't typically have the kind of a priori knowledge that an HPC application might have to be able to set the schedule. So the scheduling problem becomes much more difficult because we really don't know what's being run on them. Okay, so there were several of these. C-through was from Carnegie Mellon. Helios was from our group, and this other one. And these all were predicated on optical circuit switch technology based off of effectively provisioning switches developed by companies for optical networking. And those provisioning switches ran about 10 millisecond time scale. There's several vendors that had those. We happen to have one actually at UCSD from another project that we used for Helios. And the key insight here is that you can't set these up and tear them down any faster than tens of milliseconds. And that then pushes you into a regime in the network that you must have your flows aggregated enough so that the burstiness of that matches this the speed of the circuit switch, or this just isn't going to work. Meaning that if things are changing faster than 10 milliseconds, forget it. You just can't keep up with it. So this is great for hotspot scheduling. It would be great in a wide area network like the B4 network that Google's building, because their control plane is running at a minute. This is plenty fast enough when you've got a control plane running at a minute. Plenty fast enough, okay? But if you're trying to push further and further down, closer and closer to the processors, in other words, if you're trying to work at the TOR level, this isn't going to work. It's just not fast enough, okay? So because of that, we developed a fast circuit switch about 1.5 years ago. And I'm just going to briefly go over how this works. It's a ring. So it's a ring-based topology. It's broadcast select. The broadcast for every single end host is one wavelength. So in this configuration, there are 24 end hosts. Each end host has a unique wavelength. All 24 wavelengths are in that ring. All 24 wavelengths get dropped to every single one of 6 nodes. Each of those 6 nodes has 4 end hosts. 24 wavelengths come in to each node. There's something called a wavelength selective switch. It takes those 24 wavelengths and selects a subset, any subset, of 4 wavelengths out of those 24 and routes them to the end host. Okay? So at every single one of these nodes, and let me go. So that's if people are interested in the technical details, this just came out in Photonics Technology Letters. I can give you that reference later on. So let me just go through that again in terms of, this is a station. There's 6 stations. Each station has 4 end hosts. Each end host transmits its own unique color. Those go up. These are just attenuators to adjust this is just power balancing. They get multiplexed. There's 24 colors coming through here. These colors that have come all the way around get dropped so they don't interfere with the ones I'm injecting. So these get dropped before these ones come in. 24 come around. All 24 come into this switch. It's a wavelength selective switch and a subset of 4 wavelengths that I can completely control. In fact, I could route one to all of them if I wanted to. Can go to any one of these ports. So while the physical topology is a ring, the logical topology of this network is a mesh. Okay? And it supports broadcast. Okay. This is what it looks like. So we have 24 end hosts in a rack. Each one of them has its own receiver, transceiver, fixed wavelength. We have lots of amplifiers because since we're dropping all 24 at every single node, this is a research network. This is not a production network. So this is all the hardware. In fact, the graduate student who built most of this hardware is here today. And it was a Herculean effort to put it all together. And this is all basically the plumbing. But we show this slide as this isn't, we built this. It's running. It's been running for a full year. And it hasn't gone down because pretty much everything that we're using is telecom, and telecom has amazing reliability. It's remarkable. Okay, so I want to just go through how this actually works. Now you know that I'm not actually a computer scientist because I'm showing eye diagrams and things like that. But basically, This is the trigger. So this is the trigger that says switch. The trigger comes in, and 3 microseconds later, the switch actually starts changing state. So this is on. You wait 3 microseconds. We can dial that out in our control plane. The switch starts switching. So it goes off and stays off for about 2.5 microseconds. And then it comes back on again. This is associated with, I'll just briefly talk about the technology. These are tiny little mirrors. What's actually in here is the same thing on a TI, a Texas Instruments projector. Okay, it's called a DLP, but they're tiny little mirrors and they only go binary. Boom, boom. That's why they're so fast. They're small and fast. They switch in about 2 microseconds, but then they ring. Because basically we took a voltage and we went wham. So they hit the stop and then they do this. So this is the ringing. So somewhere about here it stabilizes enough for the clock data recovery to set. Okay? So you got about 2 microseconds of true physical delay, which is pretty fast. By the way, that 2 microseconds is the same time it takes me to pull my stupid cues out of my NIC. Okay? So about 6 microseconds of ringing, and then the CDR, the clock data recovery, locks. And we know that because of this curve. So this curve, which the details of how this curve are in the paper, is the system level switching time. This is not the 2 microsecond switching time that I showed in the previous slide. This is sitting at the NIC. We're using Miracom NICs, and we're using one of their APIs to look at the packets that are coming in to the NIC queues after everything. That includes all of the physical delay, all the CDR lock, and what Nathan Farrington actually made this measurement with help from Alex. What they did is they actually just started blasting data out, started switching, and they started watching where the drop packets were. And based off of the gaps in the drop packets that they saw in the input queues to the NIC, they got this histogram of the overall switching time. So this is the physical level, this is the network level switching time of that optical circuit switch as a mean of about 11 microseconds. What I want to emphasize about this is that is on the order of all the other delays that we're dealing with, right? So this isn't even an order of magnitude slower than the delay I have to deal with in terms of pulling my PFC frames, right? So when someone asks me, oh, we need a nanosecond optical circuit switch, I just look at them and go, why? If it's taking me 2 microseconds to get stuff coming out of my NIC, why am I building a circuit switch that's running at 10 nanoseconds? Okay? And that's one of the key insights that we have is I don't think you need, at least for 10G data, I don't think you need that fast a circuit switch. Okay. So I'm about out of time. I want to wrap up with some conclusions. So everything depends on your assumptions. Okay? The key assumption of hybrid is the 80-20 rule, or the 90-10 rule, whatever rule you like, which is that most traffic is carried, or most of that traffic matrix is in a few of those entries. And the key insight of hybrid networking is if those entries that are carrying most of the traffic are persistent enough to be able to find, identify, and schedule, then I can take all of that traffic in those persistent flows and route them over a circuit and still have all of my features of my packet-based network sitting right alongside it. Okay? This type of approach is absolutely complementary to the trend towards software-defined networking. So you can just think of an optical circuit switch as another resource that a logical network can use for a certain class of traffic. You could certainly envision that you would just build this as an overlay network that for this one class of traffic, you just say this class of traffic, circuit switch. Okay? And you still have the same logical control plane that Amin talked about yesterday. Where you deploy it depends on many, many things. Okay? As I said, is if you're way up at the aggregation level or you're all the way up at a border router where the traffic is stable enough, you can use commercially available technology right now because the control plane isn't running any faster than the optical circuit switch is switching. As you push it closer to the TOR, you've got to speed it up. And when you start trying to run your control plane on the time scale of tens of microseconds, you can no longer use a standard Linux kernel, you've got to start implementing your control plane in firmware or hardware. That's why we had to use Vertex 6s for our control plane. So whether or not it makes sense to deploy at the Tor level or even below is an open research question. And we're actively looking at that. We're actively looking at how you might be able to, and what the issues are if you continue to try to push this type of topology closer and closer to the end host, or ideally, obviously, closer and closer to the processor. So with that, I'd like to acknowledge the numerous sponsors on this work. We've had sustained support from an engineering research center at NSF. Several of the members of the faculty have a Center for Network Systems. We've had significant support from a variety of companies, Cisco here, Google, Corning, which is one of the largest fiber manufacturers in the world. And I'd particularly like to call out Mindspeed, because Mindspeed helped us build the electrical circuit switch. They actually dedicated engineering support for us to lay out that board to use in REACTOR. So with that, I thank you for your attention and be happy to take questions.
Hey, so that was a super interesting talk, George. Thanks a lot. Questions? Okay, Fabrizio.
You tested this on a relatively small-sized cluster, right? Can you comment on the scalability of the approach?
Great question. So if everybody heard that, is how scalable is the solution? So again, as people know, one of the real Achilles heels of all schedulers is that, for example, Birkhoff von Neumann has an n-cube complexity. So if we actually tried to, without doing things fancy, if we tried to continue to scale, the optical circuit switch has beautiful scaling properties if it's what I call a space switch, because the data rate per port is agnostic, doesn't care. So in that sense, it has great scaling properties. I think the limit to this is, again, going to be in the, so we know we can control the burstiness, but if we slow stuff way down, and people go, well, it's terrible. You're slowing it down to 20 microseconds. Remember what the talk from Cisco said is every single hop in your packet switch network is about 10 microseconds. So for me, queuing stuff up in my end host at 10 microseconds is the same as one hop. Okay? But having said that, if you're trying to build a schedule for a small data center in Google's world of 30,000 end hosts, okay, you cannot, at least in my opinion, take the whole schedule. What you're going to have to do is you're going to have to do some sort of factorization of a local schedule and a global schedule. And that's currently something that we're looking at. I think the limit to the scalability of this is actually the closed loop of the traffic estimation, getting the schedule, and implementing the schedule quickly. I don't think the limit is in the scalability of the optical circuit switch, because that has very nice scaling capabilities. Okay? So I think the limit is, can you actually execute your control plane quick enough? Exactly.
More questions?
Could you comment on applicability of the work that you've done to 100 gigabit per second networking?
Yeah, so now let's ask the flavor. So the issue with all of the numbers that I gave have to do with line rate, okay? And so the 100 gigabit standards right now are all multiples of 25. So either space muxed or wavelength muxed, it's 425s, okay? I'm not going to talk about the 1010s. Let's just 425s. You would have to take all of our numbers and divide them by 2.5, okay? What does that say about the optical circuit switch? Again, depending on how much I can burst, I still believe that at 100G with a 25G line rate, okay, we may, I'm not going to definitively say that, we may be able to get away with circuit switching still on a microsecond time scale, okay? To my knowledge, nobody is talking about a faster line rate on board than 50 gigabits per second, simply because of the limitations of FR4 and so on. So I'm not so concerned about aggregate rate. I'm always concerned about line rate, right? And so Worst case, you'd have to take these numbers and probably scale them by a factor of 5, okay? But again, depending on where we're at, if I can batch up enough to slow it down, right, then maybe I do have to push across a microsecond. But even at 100G with a 50G line rate, I don't think I have to be at a 10 nanosecond time scale for my circuit switching. Again, just based off of what we know about 10G today. Okay? Does that answer your question?
I just have a very short comment.
Okay.
It will take longer to lock your CDR at those higher.
Yeah, so let's talk. That's a great question. First of all, the locking the CDR is an incredible headache. When we first got these things, they were doing these stupid equalization from the PHY chips and so on. So let's just be clear about this, right? The standards for PON have a 400 nanosecond lock time in the standard. Okay? We know there's technology that can lock in sub-microsecond. Whether we have it in our system is a different story. So at the level that I'm concerned about this, and believe me, we're concerned about this all the time. That's why all of our transceivers are limiting and not linear. Yes, it's an issue, but I think there's other things that are going to slow me down more than if you could give me a custom CDR lock. Now, you're talking about, you mean at a 50G line rate. Yeah, and that's true. Yeah, even 25. So I don't know what the specs are in terms of the CDR lock time at 25. The PON spec for the standard at 10 is 400 nanoseconds. Okay? But we can probably live with a microsecond lock time on a limiting amp. Right? We don't need equalization. We don't need all the adaption because our link lengths are short enough. So if I tell somebody CDR on that, right, and I think the reason for that is their link margins are really very tight. So they're not getting a lot of power to be able to lock them. So yeah, the devil's in the details. We know this is an issue. But the question is that going to dominate over me being able to pull stuff off my end host NIC or whatever, right? And what we're seeing is all these numbers are in the range of microseconds right now. Okay? So unless you're talking about locking in 10 microseconds, I'm not too worried about it yet. Okay?
Sorry. Did you consider using something like Cavium Octeon instead of your NICs? Because then you would have done the classification in software. You would have had all the control by just GPIO pins.
We are actively pursuing other solutions besides priority flow control. Okay.
Yeah, because that seems like that was one of the Achilles heels.
It is
of your
Achilles heel. So let's just say that we were fascinated by the Tylera chip yesterday.
Yeah.
Because that Tylera chip looks like it can circumvent many of the issues that we're seeing.
I can name 6 vendors off the top of my head. Yeah.
So the simple answer is, our initial constraint was, let's see what we can do with stuff we can buy off the shelf. You buy it, you look at it, you realize its limitations, and then you iterate. Okay? We're at the point that this is what we saw. This is our first iteration. We know it's an issue, and we're actively trying to figure out how to get around it. The 8 Qs kills us. Yeah. We'd vastly prefer to have more than 8 Qs. So both of those issues, the 2 microseconds we're seeing along with the 8 Qs, we definitely want to try alternative solutions.
Yeah, with something like Tylera, it's how many Qs do you want?
Exactly.
Thousands.
That's great. For us, that'd be great because we could use a Q per end host. I mean, that'd be wonderful. Right.
Okay, George, question. How useful would it be to have a smart FPGA NIC in each of the end host machines? Like a NetFPGA 10G, for example, has 4 10-gig ports.
Right.
And will give you 10 nanosecond precision on being able to burst traffic out. You wouldn't have to mess around with the Intel NIC. You'd be able to just...
And yes, so getting back to his point, we are actively trying to ask ourselves, we don't like PFC. What's our next solution? Now that we have experience programming the Vertex 6s, right, obviously because the 10G net FPGAs are Vertex 4s, maybe we can do that. But again, we're a university. I mean, the development time to get hardware running like this is extreme. But we would love for you to help us do that.
Well, Vertex 5, actually. But actually, there's even newer cards past that one now that are out. And like the Altera-based cards that have 10-gig ports. And I mean, we'd be happy to build something like this for you if you're interested. And just maybe
so the simple answer is, in this first iteration, we identified where the long poles are. Some of them are, in CDR lock and these other things. Now the question is, what's in Gen 2, what's the most efficient way for us to try to get those out of the system and then figure out what's going on, right? So we have two 10G net FPGA cards already. We just haven't decided to, go down that route as of yet, because we had the NICs and the students, it's much easier for them to play around with the NICs than the 10G net FPGAs today, okay?
So one last question, sorry. Is that the Radix 5, is that the optimal? I mean, is that, having 4 ports coming out of the machine, would that be useful for you? Yeah,
so for us, it's just getting the data across the backplane. The whole issue is, at that speed, we're not running we can't get anything off the disk. We can't get anything off disk through the backplane out faster than 10G. Maybe someone else can, but we can't on a Gen 2 bus. So when we go up to these rates of 40G and so on, because of just the way the architecture is, we may have to do synthetic traffic. We won't be able to run real traffic based off of the end hosts we have. So the short answer is not really, because we can't run real traffic off the end hosts that we use any faster than 10G right now, based off of our current architecture. We'd have to re-architect or buy new servers that could do it.
Yeah, you do like Gen 3 PCIe by 8
right,
by
right.
16.
But these servers are about 4 years old now.
Okay.
So they're all Gen 2.
Thanks.
Yeah, so in terms of specifically why PFC doesn't work very well for you, one thing that seems clear for your presentation are the associated on-off latencies and what they do to your utilization. But it sounds like you're saying that there's a channelization, a limit on the amount of channelization that you get with PFC that you're concerned about, or some sort of headline blocking issue or something like that. I just wanted to see if you could elaborate on what else besides on-off latency you see as a concern with PFC.
Everything just evolves around the overall issue of synchronization, right? The tighter I can align my slots in my circuit to my queues, the less overhead I have to allocate for my amortization. That's all it is. So anything that's screwing me up there is just eating into effectively my duty cycle that I can send data. That's it. But the 8, from an architectural standpoint, I mean, we can't build bigger than an 8x8 system right now, right? Because we want to allocate a queue per end host, right? So in terms of, there's issues that we have with respect to synchronization. The 2 microseconds doesn't bother me because I got a 10 microsecond switch. But what bothers us more is the fact that we only have 8 queues, right? That in terms of architecturally is we've got 72 hosts. We'd love to be able to build a bigger system to maybe address some of the issues that Fabrizio was saying, is what happens when we try to scale it up from 4 to 8 to 16 hosts in terms of the convergence of the schedule and so on. But we can't do that right now because of limitations in PFC. Now, I know you guys have a custom solution, but again, we were just using IEEE standard to start.
Okay,
so.
Thanks.
You mentioned earlier in the talk that this work has interesting implications for the NIC itself and the capabilities on the NIC. Can you expound on that a little bit? Right.
So I think one of the things that this whole work says is the NICs need to be smarter, right? The fact that that batching is occurring and it's totally opaque to us, okay? The other thing is on the Miracom NICs, it comes out just fine, and I don't even remember where the number is, but somewhere around 7 or 8G, it decides to start batching. And we don't even know where that is, right? So it's going along just fine. So then, we can see we put a packet out, it goes into the NIC, and it comes out at a relatively deterministic time. And then all of a sudden, depending on the rate, internally it starts batching, and we have no idea. And then we start to see these batches of packets coming out on the wire. That kills us, right? Because of the synchronization. We want deterministic control over that aspect of the network. And right now, that part of the network is opaque, not because, if they gave us the source code, we could probably find it. But again, for us, that's an opaque part of the network which is causing uncertainty in terms of our synchronization. And so smart NICs.
So maybe I can answer that. So to defend the NIC, it's not the NIC's fault. So if you are sending 1500 bytes MTU at 10 gig, that's less than 1 million packets per second. everybody can do that. It's not very hard. It's TCP. So TCP is a dog, and so TCP segmentation offload, the goal is to have a bigger virtual MTU to pass through TCP.
Right.
So the NIC is doing what TCP cannot do, but the batching comes from that. So in a way, it's good for you. It's good for you that you need bigger batches to get more efficiency on your circuit switching. TCP wants bigger batching because TCP is slow in design.
Right.
So you have a big ally behind you, which is the TCP inefficiency, and will stay with you forever. So the bigger the batch, the better it is for TCP, and the better it is for you. But the NIC has nothing to do with it.
But I would still like to be able to control that. Yeah, I would still like to be able to control the parameter of the TCP offload engine so that I know what it's doing. Right now, we figured it out, but it's a black box to us.
But it's not a TCP offload engine. It's a TCP segmentation offload.
Sorry,
so it's the driver, the TCP stack, that decides how big is that batch.
Right.
On Linux, it's 64K max.
Right, we know that. So, but again, if you go back, if you just took that all apart, I would like to be able to just even have access to that piece so that I can play with it, right? Because now what's happening is we've got that piece, and then we have software, so we can batch in software. I'd like to be able to decide where to do that, as opposed to just dealing with that. Because I could pull that if I pulled all that off of the hardware off the NIC and stuck it on one core of the processor, I could still do this, but then I could coordinate it perhaps better with my software batching, right? In other words, I could have a unified way of deciding how big it is. Again, under the constraint, like you're saying, is it, as I play around with this, it's going to affect the overall end-to-end performance, right? So, but I want that knob, and most people don't.
So that's why I'm saying there is no hardware batching. The decision is pure software.
Well, I don't know how, then I need to know, you have to show me where I can adjust it. Okay. Because right now we can't adjust that, right? It's, at least in the Intel NICs, it's blind to us. In other words, it does it, and we have no control. We can control the size that goes to it, but we can't control what it does inside it. But again, we don't have source code. So we're just taking the driver as it is, right? Okay.
I'll get the coffee right.
Right, thank you very much.
Okay, that was a super interesting talk. We could tell by all the questions. So thank George. Thank you a lot.
Thank you.